This is chapter 12, lesson 2. This one is called the solution process. So it's going to be real similar to what we did yesterday or the day before, whenever you did the last lesson. I don't know. So here what we're going to look at is we're going to look at ways to affect the solution process, different factors that can affect the rate at which something will dissolve. We are going to look at solubility and saturated versus supersaturated solutions, and a couple other things as well. We'll look at the difference between like dissolving a solid in a liquid and dissolving a gas in a liquid, because they do behave differently a little bit. And at the very end, we're going to look at the lab that you should be doing the next time you meet. All right, so I am going to post these notes again, so if you're not getting everything while I'm going through the notes, you can for sure go write stuff down later. Okay. So these three factors tend to affect the rate at which a substance will dissolve, specifically when you're talking about dissolving a solid into a liquid. Okay, so by increasing the surface area, you're going to dissolve it faster. To increase the surface area, usually that means that we're going to cut it up. We're going to cut it or crush it. Okay, that means that we have more area for the solvent to attach and to pull apart the molecules of these solutes. Okay, so increasing the surface area, cutting or crushing. Agitation. Agitating means to either stir or shake, and that is going to speed up the rate of dissolving, because again, you're continuously bringing fresh solvent in contact with your solute particles. And then temperature, if you think back to kinetic molecular theory, temperature means that the molecules are moving faster. So the more they're moving, the faster you're going to dissolve, because you're getting more solvent contacting the solute. And so higher temperature is going to speed up the process of dissolving. We can describe this, how well something will dissolve in another something, how well one thing dissolves in another thing. And when we are describing that, we say we're describing the solubility. Okay. So with solubility, what we're describing is once we reach solution equilibrium. We've already talked about equilibrium before. In this sense, again, we're talking about dissolving a solid mostly in a liquid. Okay, so the dissolution, the dissolving, and the crystallization are occurring at equal rates. Okay, so the same number of particles are dissolving from our solid as are recrystallizing. Okay, so it may not be the same particles that are going back and forth, but the same number of particles are going one direction and the other direction at the same rate. Okay, so that's what we mean by solution equilibrium. So we can describe this in terms of saturation. If I have a saturated solution, I have dissolved all that I possibly can at that temperature, at least. And so I can't dissolve anymore. If I try to dissolve anymore, it just settles to the bottom. So in particular, we would be looking at like dissolving salt into water, right? That's our common example. You eventually reach a point where it doesn't matter how much you stir it or anything, there's salt on the bottom and it will not dissolve. Okay, so you've reached your equilibrium and you are saturated. Unsaturated means that I can still dissolve more. Okay, that I can stir it or whatever, and it all dissolves. Okay, and supersaturated means that I have more solute than a saturated solution. Supersaturated, you can't do under all conditions. Okay, and not every substance can undergo or become a supersaturated solution. Supersaturated, usually what has happened is that you have heated up your substance and dissolved it. So remember we said temperature affects what will dissolve. or how quickly it'll dissolve. It can also affect how much can dissolve. And we're going to look at that in just a second. So if you heat up your substance, you can usually dissolve more. So to make a supersaturated solution, you heat it up, dissolve the maximum amount, create your saturated solution, and then let it cool. And what happens with a supersaturated solution is that then if you agitate it at all, or you add even just one crystal, the whole thing like crystallizes. Sorry, I lost the word. Okay, so if you disturb it at all, the whole thing crystallizes. You can sort of do this. It's not quite the same thing, but if you take a water bottle and you put it in ice, like just like put it in a really cold environment, you don't quite freeze it, but you just put it really cold for a while, and then you take it out and you hit it really hard on the table, the whole thing will turn to ice. Okay, but you have to get it really cold. And it's a similar process. It's not the same thing because you don't have a saturated solution with water, because it's, you know, water. Okay, this is a video. It's called Hot Ice. This is sodium acetate. And we're going to watch this, and it's a super saturated solution. It's really kind of neat. Okay, so has some exciting music. So we have this liquid solution of the sodium acetate. Okay, and so it's been disturbed, so it's starting to crystallize. So then the whole thing crystallizes. Okay, and so then I think he's got oh, he's gonna keep pouring onto it, so you can kind of build onto it. And you, as you pour it on there, it just is going to start crystallizing. So he just kind of pours for a little while. I say he, I don't know the gender of the person making the video. I'm guessing. And so he's going to pour a little bit more, I think, just to kind of show you that he has the same substance here. So it's called hot ice because it looks like ice, but it's at room temperature. All right, so that finally fell over. So he's going to pour the liquid in this time. And I think in the first one, there were maybe crystals already in the bottom, which is what disrupted it and made it crystallize. So now he's going to take just a tiny amount and drop it in. And then that causes the rest of it to crystallize. I don't know if you can hear me over the music. Sorry. So that's what happens with a supersaturated solution. So sodium acetate is one solution that you can do that with. There are others. That's the end. So we're just going to stop. So that's a supersaturated solution. They're kind of neat. So we can describe the solubility of substances. So solubility, we talked about that as the ability to dissolve. And so what we're talking about when we're discussing the solubility of one substance in another substance is how much of the solute do I need in order to form a saturated solution? And this is temperature specific, and it's also going to depend on how much of your solvent you have. Uh, so usually when we're describing this, we're gonna, our amount of solvent is gonna be like 100 grams of the solvent, 100 grams of water or whatever. Okay, and we will look at graphs here in just a second, I think, to see. We're gonna look at graphs of different substances and their solubilities. And that's usually how we would share that information, is that's a graph over a range of temperatures, what's happening to the solubility. To predict whether or not something will dissolve in another substance, the solubility, we say like dissolves like. So like, what we're describing here is the nature of our solute and solvents. Okay, so whether or not they form charges is basically what we're describing. So if you have something that is polar, a polar solvent like water will dissolve polar solutes and ionic solutes, okay, because they both have charges. Remember, polar means that some part of the molecule, some element is pulling on the electrons more and some element is pulling on them less, okay? So you create regions of charge within the molecule. Ionic, remember, breaks apart into their ions. So you have these charged particles. Okay, so charges, anything that's charged, will dissolve in a polar solvent. Nonpolar solvents will only dissolve nonpolar solutes. So like oil is nonpolar. It doesn't have any charges along the molecule. So you can't dissolve oil in water because water is polar. And that's why they don't mix. Okay, so polar will dissolve polar and ionic. Nonpolar will only dissolve nonpolar. When you're describing two liquids being soluble or not soluble in each other, instead of saying soluble because they're just mixing, we have a different word that we use. So instead of saying, okay, they're not soluble or they're insoluble because they don't mix, they form these two layers, what we say is immiscible. Okay. So a substance that won't dissolve, if you have two liquids that won't dissolve and instead they form layers like oil and water, they would be said to be immiscible. So oil is immiscible in water. Here's another example. This is toluene. Toluene is, I forget what it's used for. I want to say paint thinner, but I'm not sure that that's right. So I'm looking to see if it describes it in the book, and it doesn't. Okay, but that's one example. That's another example of an immiscible substance in water. But if they do mix, then they're said to be miscible. So ethanol or ethyl alcohol, most alcohols, I think all alcohols will dissolve in water. Okay. And then this is carbon tetrachloride, and these two substances will dissolve in both water or polar substances. They will also dissolve or mix. They are miscible also in nonpolar substances like carbon tetrachloride because they have an end that is polar and an end that is not. Soap is very much the same way. So you can mix them with either polar or nonpolar solvents, and they are miscible in both. Okay. Okay, so now we're going to talk specifically about gases. So we looked at the effect of heating, crushing, and stirring when you have a solid solvent. But what if you have a solid solute in a liquid solvent? But what if you have a gas? So gas solutes behave a little differently. For one, the pressure is going to affect how soluble they are. Okay, so for example, soda. If you have soda under pressure, you have a lot of the molecules dissolved, and once you release that pressure, then a lot of the gas molecules escape, and that's why it gets all bubbly and fizzy. Okay, that's why especially if you have shaken uh, your soda up, you should not open it very quickly. You should either let it set for a little while or open it very, very slowly. Otherwise, you make a mess. Okay, and it has to do with the pressure. So this gives us a new law, Henry's law, that relates the solubility of the gas to the partial pressure of the gas. So the more pressure you have, the more gas you can dissolve. Okay. And so they always kind of over dissolve the gas so that once you release the pressure, some amount of that is going to escape, and that will keep some of your fizziness to your soda. Okay. But once you release the pressure, then a lot of that gas that's dissolved forms its gas bubbles, and that's why it gets all foamy. Because we say it's coming out of solution. So that's how pressure affects solubility. Temperature also affects solubility, and we talked about this a little bit, that over a range of temperatures, different substances can behave differently. Typically, if you have a solid, then typically they become more soluble as you increase the temperature. You can dissolve more of it. And if you have a gas, as you increase the temperature, the solubility decreases. So that's why we keep our sodas in the fridge, right? Especially once you've opened it. If you keep it in the fridge, the gases will stay dissolved and it won't go flat quite as fast. Okay. So you can see on this chart that there are several substances. And for some reason I can't, there we go. So this is called a solubility chart or a solubility graph. So we're graphing the temperature down here, and then the solubility, the number of grams of our solvent that would dissolve per 100 grams of water. So you can see that all these substances behave very differently. So table salt, sodium chloride, is right here. It says blue line. And so from 0 degrees Celsius to 100 degrees Celsius, there's not a huge change. Okay, it goes from like 35 to 39 grams. Okay, so there's not a huge change. You can't dissolve a whole lot more just by increasing the temperature. This right here, this black line, this one is sodium acetate, I do believe. They've written it in a different form, but I'm pretty sure that that is sodium acetate, which is the hot ice that we looked at. Okay, so as you increase the temperature, you drastically change how much you can dissolve, which is what lets it be that gets to that super saturated solution. Okay, and then it kind of reaches the point where it slows down a lot. Okay, so if you heat it up a little bit and you get it to saturated level and then you let it cool, it wouldn't necessarily recrystallize immediately. Okay, so you need to be able to read one of these and just kind of generally what we would ask you to do is, okay, what's the solubility of this substance at this temperature? So like lithium chloride at 65 degrees Celsius. So you're finding the lithium chloride line where it crosses 65 degrees Celsius, and then you would read that back. And so you can dissolve 100 grams of lithium chloride in 100 grams of water. Okay. So I think you have some practice problems reading, not practice problems, but problems on your homework, reading a solubility chart. Okay. And that's the end of today's lesson. So let's go look at your homework really fast. And then we're going to go over your lab that you're doing next, the next time you meet. So for the first problem, you might need to reference a chart that shows you how much of the substance can dissolve. You're looking for the KClO3. So if you dissolve 15 grams at 25 degrees Celsius, how much it will actually dissolve. So then you're going to decide if that makes the solution saturated, unsaturated, or supersaturated. Oh, it gives you the information you need at the top. You don't need a chart. If I read, I can see that. Okay. For question 2, you will need a table from your book. You need the data in figure 2.4. If you would like to go and look at that and take a picture of it and you don't have to take your book home, totally fine with that. Question 3 and 4 are based on a different figure. And then the backside is all multiple choice. Okay. So 3 and 4 are looking at the solubility of substances at different temperatures. Okay. So you're just going to determine the solubility. How much would you be able to dissolve? And then in number 4, you're figuring out what temperature would you need for each of these amounts. Okay. So pay attention to the question and what it's asking. All right, the lab that you're doing tomorrow, I'm going to assume tomorrow, it's called the dissolving rate of sugar. So it's pretty similar to one that I think you've done before with Alka-Seltzer and determining the time it takes for the Alka-Seltzer tablets to dissolve in hot water and cold water, and if they're whole or broken or crushed. This is a little bit different though. You're going to use sugar cubes. You will need to heat up some water for this. Okay, so pay attention. I've made a couple of changes to the directions or to the materials list. So instead of using triple B balance, you're going to use a digital scale because it's faster and more accurate. You can use heat resistant gloves, otherwise known as a hot pad, or you can use some tongs to move your beaker. I think we're going to pour some water. And you are going to be testing, you have a chart, you have 4 sets of conditions that you're testing. And so you'll be either testing different temperature or different particle size or different, whether you're stirring or not stirring. Okay. So you're going to fill in the chart and then you're going to answer the questions. The questions at the bottom, you're going to need to probably answer on separate paper, which is why I wrote in answer on separate paper. If you don't have any paper because you're just really ill prepared for school, you know where I keep my paper. Okay, or you can use the backside. Backside is blank. All right, so that's what you're going to do tomorrow. You'll either be using whole sugar cubes or crushing them up, depending on which test you are doing. All right, that's your task. I think you guys should be good to go for, I probably should have stopped sharing my screen before I showed you that, and then, you know, could have actually seen it. Let me know if you're having questions and struggles with this. You'll do that lab, and then we'll do the last lesson for chapter 3. Sorry, chapter 12, it's lesson 3. That one we do split into 2 parts. That one you will need a calculator. You might need your periodic table, have it handy, I don't know. But definitely a calculator, because the math comes back. You'll be okay, I promise.